So should I start? Okay. Right. Welcome everyone. Welcome to Harvard CMSA Quantum Math Physics Seminar Series. We are very honored, delighted to have a Professor Cenke Xu from UCSB. And Cenke is a really great physicist. I have learned a lot from him in the past. Let me tell a little story. I think I sent an email long ago when I was a grad student on nonlinear signal model about his work, and he's really enthusiastically answered all my questions. And he also guided me and Ising Yu, his collaborator, learning the decombined quantum criticality. He has done a lot of condensed matter interesting works, and many insights connected to quantum field theory and duality anomalies. And recently, he want to speak about topics that I'm also interested in, quantum information. So today we are very honored to welcome him speaking about QFT and quantum information theory together. Let me remind the audience, please feel free to ask questions, and let's welcome Cenke.
Thank you. Well, I want to thank Juven for the invitation and for the very nice introduction. Well, frankly, I don't quite remember our email exchange long back, but still, I mean, I'm very glad that I've known you for this many years and had so many wonderful discussions with you. So today I will talk about something which I find very exciting just recently. It's about the quantum field theory approach to the quantum information. So let me first acknowledge my collaborators, Dr. Jiangyang Li, who was a postdoc at the KITB, but he will join UIUC as a faculty member, and Yizhuang Yu, who is now a faculty member at UCSD, and Chao Ming, who is a faculty member at Cornell, and Chong Wang in Perimeter, and Naya and Kaixiang are my students in Santa Barbara right now. Yeah, so basically, I will try to use field theory, or more generally condensed matter approaches or condensed matter techniques to address some class of quantum information problem, like the problem of decoherence and weak merriment. And actually, so in the introduction, I will try to emphasize that actually to correctly address this kind of a question, actually there are symmetry conditions that we need to be very careful about. So there are two different symmetry conditions. Some literature call it a strong or weak symmetry condition, and actually in our works, actually we call it a doubled or diagonal symmetry conditions, but they should mean the same thing. So I will explain what they mean. Then I will try to look at quantum antibody systems under decoherence or weak merriment, and in particular, I will look at several different kinds of quantum antibody systems, including quantum critical points, and also topological states, or more precisely states with nontrivial topology under decoherence and weak merriment. So is there a question in the? No. Oh, okay. Yeah, okay. So then actually, if there's time, I will also briefly mention the higher form symmetry, systems with a higher form symmetry under weak merriment. Yeah, right. So let me first explain what does the weak merriment even mean. Sorry, the screen somehow froze. Yeah, okay. So let me first explain what the weak merriment and decoherence even mean. So basically, we know that our microscopic world actually is quantum, but our daily life is actually classical. So we can ask how a quantum system actually gradually become a classical system. So the theory of decoherence says that actually a quantum system will gradually lose the quantum coherence through forming entanglement with the environment, with the ancillar qubits or the environment qubits. And actually, once the system forms entanglement with the environment, then we can actually just trace out the environment and actually get a reduced density matrix. And then the reduced density matrix actually will look classical, will look more classical. And actually, so let me take the simplest quantum system ever, just a one qubit, and let me prepare the qubit in this state. Okay, this state is actually a spin up superposition with a spin down. It's actually eigenstate of X operator, of a spin sigma X operator. And actually, let's say that actually I want this single qubit to go through a cloud of ancillar spins. and let the system have certain probability to form an entanglement with the ancillary springs and see what happens. And actually, so let me first write down the density matrix for this state. So this is a pure state density matrix, basically 1/2 times 1, 1, 1, 1. It's a pure state density matrix. Okay. And then what happens after this state? I mean, after this density matrix going through the cloud of ancillary springs and have some entanglement with the environment. So basically, forming entanglement with the environment and then tracing out the environment actually can be effectively also understood as the system being measured by the environment. So actually, the outcome of the process can in general be expressed in this form. So basically, there's a P. A P is a number. Let's say P is a small number. So basically, 1 minus 2P is actually a number slightly smaller than 1. So basically, there are 3 terms here. The first term means that actually there's a large probability for the spin to not feel anything at all. Okay, so there's a large probability for this matrix to remain the same form as before. But there's a certain probability P for the system, for the target system, the qubit, to be measured along the z direction and have measurement outcome z equals to 1. So we know in quantum mechanics, once the system is being measured, and actually the wave function will actually just collapse into z equals to 1. So this is the density matrix for z equals to 1. And then, of course, there's going to be a equal probability P for the system to be measured along the z direction and get another outcome z equals to -1. So this is the density matrix for the spin for being a z equals to -1. So that means that after this process, the decoherent density matrix will generally look like this. And suppose we just play with a little bit algebra, we can show that the density matrix will take this form. Okay, we'll take this form. The Z and X, they're the Pauli matrix. Okay, the Pauli matrix. So this is a very, very simple process for a qubit.
Excuse me?
Sorry. Okay, yeah.
Yeah, for the Zoom audience, we couldn't see your slide updating right now. Could you mirror your screen?
Actually, this is the slide I'm in right now. I didn't really move the slide. So do you see the cloud?
No.
No cloud. Yeah. It's not even in slideshow mode on the Zoom.
Really? That's weird.
Now it's moving.
What about now?
Now it works. But it's
Okay.
a speaker's view, not the full screen. So I can see your next slide also.
That's okay with me, as long as it's okay with you guys. You know, yeah.
As long as there's no secret there, it's fine.
Yeah, right. There's no secret. Don't worry about it. Yeah, right. So as long as you can see the screen, it's fine. Yeah. Okay. See. Okay. Right. So at this state, so maybe I should repeat a little bit. So basically, I started with this single qubit with this state, and the rho equals to 1/2 1 plus x. 1 is the 2x2 identity matrix, and X is the Pauli matrix, and I let the system go through a cloud of ancillary springs, and this is the outcome. And actually, the outcome can be simplified in this kind of form, okay, in this form. So the point for this slide is to recognize that there are 2 different symmetry conditions. So basically, the state I start with, which is a superposition between upspin and downspin, and this state is going to be invariant under a Z2 symmetry. I can use the operator X to act on this state. I'm going to get the same state. It's invariant on the operation of X. But then once I take the density matrix, then you can see the density matrix actually is invariant under 2 Z2 symmetries. Formally invariant under 2 Z2 symmetries. It's invariant under X operation from the left and X operation from the right separately. Okay, so it means that the density matrix, once I write the system as a density matrix, it looks like the density matrix will have 2 different symmetries. One from the left, one from the right separately. But then after decoherence, the density matrix actually will lose their double symmetry. For example, if I act from the left, it's no longer going to be invariant because the Z anti-commute with X. Okay, and also from the right side is also anti-commute with X. However, the decoherent density matrix will still have a diagonal Z2 symmetry because I can still operate from the left and the right simultaneously. Okay, and the decoherent density matrix will still be invariant, right? So it means that before decoherence, my system will have a double symmetry. But after decoherence, after being weakly measured by the environment, actually the decoherent density matrix will have a diagonal symmetry now, and the symmetry is weakened. Okay, so why does it happen? So it turns out actually, as I said, there's a probability for the system to be measured along the z-axis. So for each measurement outcome, the Z2 symmetry is broken. Okay, if I measure to z equals to 1, the Z2 symmetry is always broken. Okay, however, I have summed over both measurement outcomes with an equal probability. Okay, so once I sum up them with an equal probability, actually turns out that we restore part of the symmetry, which is diagonal symmetry. Okay, which is diagonal symmetry. Okay, but of course, I can also break all the symmetry by just post-select the measurement outcome. Okay, I can make this state has a slightly bigger chance or probability than the other state. Okay, then actually I break all the symmetry. Okay, so at least actually, as you can see that there are several different symmetry conditions. Okay, I can have a double symmetry condition, diagonal symmetry condition, or sometimes I can just use all symmetries. Okay, so it turns out that this is generally true for, yeah.
So usually when we discuss symmetry, we do define operators invariant under this conjugate operations of some symmetry operator, both sandwiched from the left and right, right? But here you separate the left.
Yeah, right. So actually, yeah. So here I define symmetry as just the density matrix being invariant under some operation. So actually later I'm going to actually map this density matrix into a state in a double Hilbert space. So basically you can just take this side, take the right, take the ket state and take a transpose. And actually, then you can write it in a double Hilbert space. Then you can see clearly that actually this new state will have a double symmetry because I can operate on the top or on the bottom. Well, anyway, so turns out that these symmetry conditions are generally true. A question?
So you call measurement that we actually entangle with other.
Yes. It's the same thing. It's the same thing. So yeah, right. So you can evolve this. You can evolve this qubit with the ancillary spin with the Hamiltonian. You can then form time entanglement. Then you can trace out the ancillary spin. You will generally get the form like this. Yeah, you will generally get the form like this. You know, it's just so this is a simpler way of writing this because I don't have to use a larger Hilbert space, right? I can just stick with the two-dimensional Hilbert space. Question? Say again? Oh yeah. Well, I mean, yeah. So let's assume this is what it does. Okay, but actually, but of course, actually, when we talk about a general quantum system, there are different scenarios which I will explain here, right? So there are different ways for the system to be entangled with the environment, right? So for example, if I start with a general quantum system, quantum many-body system, and I start with a symmetric state, this symmetric state could be quantum disorder state, SPT state, topological order, quantum critical points, all these are symmetric states, okay? So if I start with a symmetric state, then actually this density matrix will have the double symmetry I mentioned before, okay? But then actually, after going through this cloud of decoherence, okay? So just as what was asked just now, suppose the environment, okay? Suppose the environment measures the quantity of the system, which actually is invariant under any symmetry. Okay, so for example, the environment only measures the energy density, which actually is invariant under many symmetries. Okay, or actually we can say that the energy density is entangled with the ancillary qubits. Okay, so in this scenario, we can show that after going through the cloud of ancillary spins, even though the density matrix becomes a mixed density matrix, this mixed density matrix will still have the double symmetry, okay? Because only the singlet of the symmetry is entangled with the environment, okay? It's entangled with the environment. But suppose the environment is entangled with the order parameter, just like the previous case, okay? Suppose the environment is actually mirroring some order parameter, but eventually I sum over all the outcomes of the measurement. Okay, then actually I will get the diagonal symmetry. Okay, then eventually the mixed density matrix will have a diagonal symmetry. And this is and let me give another picture for what happens. Okay, so now let me enlarge the Hilbert space. Let me really take the target system and the ancillary spin as a whole quantum system. Okay, as a whole quantum system. And we know that what happens here is governed by a Hamiltonian, interacting Hamiltonian. And this interacting Hamiltonian will involve some operator from my target system and some operator from the ancillary space. Okay, and just to simplify the problem, let me think about a system with a U1 symmetry. Okay, just with a particle number conservation. And let me say that my original state has a fixed particle number. Okay, has a fixed particle number. Then in this case, you can imagine that suppose this OS and OA, both of them are singlet under the U1. Okay, then after I trace out the environment, okay, then the decoherent density matrix will definitely still have exactly the same particle number as the original state. Okay, as the original state. Okay, then actually this decoherent density matrix will still have a double symmetry. So in this context, a double symmetry means the system being involved in a canonical ensemble. Okay, in a canonical ensemble, because I do not really allow the particle number to hop in and out from the system. Okay, I only allow some other quantities to be entangled, but I do not allow the particle number to hop in and out. But now suppose I say that this interacting Hamiltonian is invariant on the U1. However, the OS and OA, they allow the particle to hop in and out. So for example, this is the B dagger, this is the B. Okay, then in this case, after the decoherence, after I trace out the environment, okay, so every eigenstate of the density matrix will still be an eigenstate of the U1 particle number. However, different eigenstate will have different eigenvalue. Okay, so that means in this sense, we can also say that actually now the density matrix evolves in a grand canonical ensemble. Okay, in a grand canonical ensemble. Okay, so the double and diagonal symmetry can have this kind of a simple condensed matter version of interpretation once we consider, for example, just a U1 symmetry. Okay, right. Okay, so now let me try to compute. Okay, try to compute the density matrix and decoherent density matrix. Okay, so well, I mean, in condensed matter literature or quantum field theory literature, we know very well that actually the ground state density matrix can be formally expressed like this. And actually, let's say that I want to compute the density matrix, the matrix element between two field configurations, phi1 and phi2. Okay, so let's imagine that I have an Ising spin, okay, Ising spin system. And actually, this density matrix is a, so every matrix element is a matrix element between two Ising configurations. So phi1 is one Ising configuration, phi2 is another Ising configuration, okay? So how do I calculate this matrix element? Basically, what I do is to perform a path integral, okay? So I just take an imaginary time or Euclidean space-time path integral with the action. The action is derived from the Hamiltonian. And actually, I just fix phi x tau equals 0 equals one configuration, and phi x beta equals to another configuration, and eventually take a beta to infinity. Okay, so suppose I can perform the path integral exactly. Okay, then I know exactly the matrix element. Okay, but actually, more often than not, we cannot perform the path integral exactly. But actually, in condensed matter, we know a lot of tricks or approximation method to perform the path integral approximately. Okay, and sometimes we can do RG calculation to find a fixed point, which means that actually the UV details do not really matter anymore. We just need to know the IR fixed point. Okay, so this is a goal of the talk. So I'm going to try to use this field theory formalism to understand what happens with the decoherence and the weak merriment without knowing too much of the UV details or microscopic details of the system. Okay, so this is the pure state density matrix. Then what happens with the decoherent density matrix? So as I said before, the decoherent density matrix, I mean, just from our earliest example, you can see that decoherent density matrix actually correspond to, I mean, there's a number times the original density matrix plus maybe a small probability times some operator from the left and operator from the right. And this operator operating from the left and right, they are generally called the Krauss operators. Okay, so in general, under decoherence, the density matrix will look like this. Okay, there's a Krauss operator from the left and a Krauss operator from the right. And actually, you can see that a Krauss operator operating from the left is like operating at one temporal boundary. Okay, at tau equals to 0. And the Krauss operator operating from the right is like operating only on the other temporal boundary. Okay, on the other temporal boundary. Okay, and now let's imagine there's a big factor, so let's imagine there's a big probability for the system to be not mirrored at all. Okay, so it means that there's a 1 minus 2p times rho plus some small perturbations. Then I can always exponentiate that small perturbation to the action, to the exponential. Okay, is that right? So 1 minus x I can always approximate by exponential x. Okay, so once I do that, then these Krauss operators on the left and right can be absorbed into a new action. okay, into a new action. And this new action will only involve terms on the two temporal boundaries. Okay, only involves terms on the two temporal boundaries. Okay, is that right? So it means that in this field theory formalism or the Euclidean path integral formalism, we map the quantum information problem of decoherence to a boundary problem. Okay, to a problem of a boundary. Okay. Okay. So now actually we can just ask, okay, we can just ask what kind of system, what kind of a quantum many-body system can potentially have interesting physics under weak merriment or decoherence. And then this question becomes, what kind of a quantum many-body system can have interesting physics at the boundary? And this answer is very standard. Okay, we know very well that actually, topological states like a Chern insulator or a symmetry protected topological state will have interesting boundary physics, right? So it means that these states actually probably will have interesting physics under weak merriment and the decoherence, because the decoherence and weak merriment is mapped to the temporal boundary. Okay, the temporal boundary. But actually, we can, usually we can do a space-time rotation, then actually the effect will become a spatial boundary as well. Okay. And another classical question with interesting boundary physics is quantum critical point. Okay, the quantum critical point will also have a boundary criticality, which is also an interesting problem that we will discuss. Okay, in this talk. Question?
So like your system goes through a channel, but like why the field is the same, like psi 0 is like psi 1, and psi theta is like psi 2.
Oh, that's the constraint for the path integral, right? So
You don't change the.
Yeah. We don't change the two boundary condition.
Okay.
I just sum over all the path in between, right? That's the path integral, right? Suppose I want to calculate the rate of the propagation from one point to another point. I fix the initial point and final point, but sum over all the path in between.
Right. But the two fixed points, they are not changed by the channel.
No. So
Because if you look at the condition, like under the integral.
Yeah, they are not changed. I mean, so let's say that this is the density matrix, which has a probably non-zero matched element between any configuration, right? I just want to look at one specific matrix element, which means that one specific matrix element means that I want to calculate the matrix element between two specific configurations. So I always fix the configuration. Then I perform the path integral in between. Right. Okay. So yeah, and also the symmetry condition actually will become very handy. Okay, here, because actually in field theory we know very well that actually we don't really need to know too much about the details in the UV. Okay, to get there, but we definitely need to know the symmetry. Okay, to write down anything in the field theory. So it means that the symmetry condition I wrote down before, the double symmetry or the diagonal symmetry will determine the form of this guy. Okay, determine the form of this guy. Okay, but once we know the form of this new term of the action, we can run RGE and try to find the fixed point. Okay, try to find some universal physics. Okay, this is the basic formula. Okay, we are going to use. Then I'm going to try to use this to different kind of problems. Okay, so let me first start with the quantum critical point. Okay, so what this means is that I will try to prepare a quantum critical state, which is symmetric state. Okay, I will try to let it go through a cloud of ancillary spins. Okay, and I'm going to ask what happens. Okay, what happens when after the system going through the quantum channel. Okay, the decoherent quantum channel. And actually, well, this is very basic. So basically, for a large class of a quantum critical point, it can be described by the Ginzburg-Landau theory. Okay, some 5-4 field theory. So basically, a small d-dimensional quantum critical point can be usually, not usually, but a large class of them can be described by the same formalism describing the classical phase transition in the d+1 dimensional space-time. So basically, here the R is a mass term for the boson, for the bosonic field, for the bosonic order parameter. When R is greater than 0, we are in the disordered phase, symmetric phase, and when R is smaller than 0, the system is ordered and it enters a spontaneous symmetry breaking. And for this section, let me assume that this phi is an ON vector. Okay, the system has ON symmetry. So let me try to consider the ON Wilson-Fisher fixed point under the decoherence and the weak merriment. Okay, so yeah, as you can see that actually we are going to make connection to the boundary of the system. So let me first review some basic properties of a boundary critical point. Oh, but by the way, let me make a reference here. So first of all, so it was this paper which actually was done by the Berkeley group. They first used this bulk boundary correspondence to study the 1+1 dimensional Latinder liquid under decoherence. And actually, so there actually the boundary or defect physics of a 1+1 dimensional Latinder liquid was understood long back in the 1990s. So today I will try to focus on a higher dimensional case. So it turns out that a higher dimensional quantum critical points and their boundary actually was understood amazingly only in recent years. So I will review this. So let me first just look at a d-dimensional quantum critical, sorry, a d-dimensional classical critical point. Okay, so let's say that this is my d-dimensional classical phase transition in the bulk. And actually, you can see that the system will have two tuning parameters. Okay, two tuning parameters. One is the R, is the mass term in the bulk, and I want to fix the bulk mass term to be 0. Okay, so I'm going to look at this line. Okay, but then there is an extra mass term as the boundary. Okay, at least there can be an extra mass term as the boundary, and I call this the extra mass term with epsilon phi square. And by the way, this epsilon has nothing to do with dimension. Okay, so don't make any connection with a 4 minus epsilon expansion or anything like that. Okay, so this epsilon is just a number. It's the extra mass term as the boundary of the system. Okay, so suppose epsilon is greater than 0. Okay, suppose epsilon greater than 0. So this means that actually the boundary does not like ordering. Okay, the boundary does not even like to be as the critical point. Okay, so it means that even though the bulk is critical, the boundary seems to have a mass term. Okay, but now suppose I measure the correlation between the order parameter near the boundary. Okay, near the boundary. Okay, you may think that I may just get a exponential decay, but turns out it's not the case. Okay, because actually the bulk is critical. Even if the boundary has an extra mass term, if I measure the correlation function near the boundary, I'm still going to get a power law decay. Okay, but the decay power or the scaling dimension is going to be much bigger than the bulk scaling dimension. Okay, so for example, when the dimension d is large, the bulk scaling dimension will be this. Okay, d minus 2 over 2 to the mean field number. But as the boundary scaling dimension will be d over 2. Okay, it's greater than the bulk scaling dimension. Okay, greater than the bulk scaling dimension. So this was understood a long time ago. Okay, this was understood a long time ago. But what's tricky is what happens when epsilon is negative. Okay, so when epsilon is negative, it means that the boundary likes to order. Okay, for some reason, the boundary wants to order even before the bulk. Okay, this means that actually when the capital D is very large, you can imagine that when epsilon is negative, the scenario can be like this. So the boundary orders even before the bulk. Okay, so there's a line of a boundary phase transition. It means that the boundary ordered here, but the bulk actually has not ordered yet. Okay, so this happens when D is large. But you can immediately tell this phase diagram is problematic when capital D equals to 3 or when the small d equals to 2. Okay, the reason is that when the bulk is a 3-dimension, the boundary is a 2-dimension. And suppose I have an ON system, we know very well the ON system cannot order, okay, at 2-dimension at all. Okay, so it means that actually no matter how negative the epsilon is, okay, the boundary definitely cannot form any order before the bulk. Okay, but then actually there's another question that because the bulk actually is critical. Okay, so I actually cannot just integrate out the bulk and look at the boundary as a local system. Okay, so they say there seems to be a dilemma here. Okay, so when epsilon is negative, what happens? Okay, what really happens? So it turns out that this actually was a tough question. It was only understood just a few years ago. Okay, by Max from MIT. Yeah, so it turns out that there's still a difference. There's still a very clear difference between epsilon being positive and epsilon being negative. But when epsilon is negative, the system does not form long-range order as the boundary. Instead, the system forms something which is called extraordinary log. Okay, extraordinary log. It means that in this side, actually the phi will almost order. Okay, will almost form long-range order. It decays extremely slow. Okay, decays extremely slow. So normally the correlation function will either have a long-range correlation or short-range correlation or power law decay, but this is different. Okay, this decays extremely slow. Okay, it's a new scaling. Okay, so I mean this. Well, of course, the boundary criticality was a very popular subject in the early 80s, but back then the numerics actually was not that great, so people really didn't really see this behavior. But actually, after Max proposed this, actually it has been seen numerically. Okay, it has been seen in modern day computers. Actually, so it's much better. So people have seen this numerically. Okay, so this is a review of a boundary criticality and the recent progress. So let me come back to our problem. Okay, so our problem is that we want to prepare a Wilson-Fisher critical point wave function, and then actually a weakly married, or let it decohere through some ancillary strings, and then look at the mixed state density matrix. And let's say that I still want to calculate correlation function. Okay, let's say that I still want to calculate something like this. Okay, so for anything which is directly observable, I need to take a trace. Okay, I need to take a trace of the density matrix. Okay, so once I take the trace of the density matrix, it means that I'm gluing the path integral, and I'm gluing the two temporal boundary of the path integral. Okay, is that right? Because actually, the left side corresponds to 1 tau equals 0, the other side corresponds to tau equals beta. But once I take a trace, it means that I'm gluing them together. Okay, so now if I want to calculate anything which is observable, the trace rho times some operator, it's like I'm performing a path integral in a cylinder, okay, but I insert a defect, okay, I insert a defect. So the cross operator now becomes a defect, okay, in this 2 + 1 dimensional space-time. I insert a defect as the 2 + 0 dimensional slab, okay, at tau equals 0, okay. And also, let's say that the weak merriment has a diagonal ON symmetry. Okay, has a diagonal ON symmetry. So knowing that it has a diagonal ON symmetry, then the extra terms I mentioned before, which only involves tau equals 0 and tau equals beta, okay, will contain terms like this. Okay, obviously we have terms like this. So this term, the last term is allowed. Okay, when the system has a diagonal ON symmetry. Okay, has a diagonal ON symmetry. Okay. But actually, once I take a trace, actually, the diagonal ON symmetry doesn't really matter that much. Okay, so all these terms together will contribute as an extra master. Okay, extra master as the defect. Okay, extra master as the defect. So it turns out that the extra, the extra 2-dimensional defect with the extra mass term inserted in a 3-dimensional path integral. This was also considered by Max, the same group, and they also showed that the extraordinary log correlation still exists. Okay, still exists with a negative epsilon. Okay, with a negative epsilon. So based on this connection between the boundary and the decoherence, we can make a very simple prediction. Okay, make a very simple prediction. So suppose I take a prepared Wilson-Fisher wave function, Wilson-Fisher fixed point wave function, and perform weak merriment on it. Okay, so after I'm doing this, I will get a mixed state density matrix. Okay, but in this density matrix, if I measure the correlation function, I'm not going to see Wilson-Fisher fixed point correlation function. Okay, I'm going to see either this or this. Okay, depending on the sign of epsilon. Okay, so without knowing anything about the microscopic details, as long as we fix certain symmetry of the weak merriment or the decoherence, okay, I can make a prediction. Okay, it can be either this or that. Okay, it can either this or that. Okay. Okay, so this is the first example. Okay, this is the first example, and we can see that field theory can indeed give us some universal answer to some question. Okay, of course. Yeah.
What happened then? Absolute 0.
Yeah. So this is called the special boundary condition. So it's so this point is not so far away from Wilson-Fisher, but still there's this correction. You can do dimensional. So you can do formalism epsilon expansion to start the part, but there epsilon is with a dimension, and yeah, right. So this also started, but actually I try not to focus on this point because this requires a little bit fine tuning. So yeah. Anyway, so we can also look at quantities which are interesting to quantum information. For example, the Renyi entropy. Okay, the Renyi entropy basically just trace rho square and then take a log. Okay, take a log. So basically, I suppose rho is a pure state density matrix, then trace rho square will always be 1, and the Renyi entropy will always be 0. okay, will always be 0. But actually, after the density matrix becomes a mixed state density matrix, then actually we will get some Rayleigh entropy because the trace row square is no longer going to be 1 anymore. Okay. Okay, so let's still perform our field theory and a path integral formalism to calculate this second Rayleigh entropy. Okay, so the trace row square, it means actually I'm going to do a path integral for one row from tau equals 0, tau equals beta over 2. And then there's another row from beta over 2 to beta. Okay, from beta over 2 to beta. And then the extra terms coming from decoherence will be applied to this defect and this defect. And there will be long-range interaction between this defect and this defect. Okay, so this is a completely new problem now. Okay, so it's like I'm inserting defect in the path integral, but I'm turning on some very non-local long-range interaction between them. Okay, between them. Okay, so actually it turns out that this is a slightly more complicated problem to calculate in the field theory, but actually we can still do some RG and get some sensible answer. So actually there's a very rich possibilities. Okay, there's a very rich possibility. It turns out that sometimes, depending on the strength of the decoherence, there could be a phase transition. Okay, there could be a phase transition which spontaneously breaks a double symmetry to a diagonal symmetry. Okay, there could be some symmetry breaking, spontaneous symmetry breaking phase transition driven by the strength of the decoherence, but this actually can only be revealed in the second Rayleigh entropy. Okay, something like this. Okay, a question?
So if I want to take the three index,
Yeah.
separate beta to
Yeah. There are many topics. It's going to be a complicated but also interesting problem. Okay, it's like you cut them into different pieces, and there are many complicated interactions between them.
But is that doable by dictionary?
Well, actually, to calculate it exactly is going to be horrible, but to do some RGE, it may not be so bad actually. And in that case, you may find some scenario where actually there could be phase transition with spontaneous breaks on replica symmetry or something like that. So there are many possibilities that can happen there. Yeah.
Okay, and this become a way to explain like the like measurement fields in terms of phase transition.
Yes. Yeah. This is the next example, I think. Yeah. So right. So let me. Oh, sorry. So if you mean the Merriman-induced phase transition, you mean the quantum circuit? Yeah. Right. So yeah, that is a very different problem from this. So that actually means that so in that kind of setup, we let the system evolve and measure and evolve and measure. Eventually, we will look at the steady state, right? But this is going to be our short time evolution. It's a short time. So it's like I let the system evolve a little bit of time, and then I see what happens. So that is a long time or the steady state kind of a problem. It's different from this. So that also has a boundary to bulk mapping, but that's a different problem. Right. Okay. So yeah, right. So just to illustrate the double symmetry, spontaneous break to diagonal symmetry, this kind of idea. So let's take a specific example, which is just a Z2 paramagnet, just a Z2 disorder state. Okay, disorder state with a Z2 symmetry. And actually, suppose I want to calculate something like a second Rayleigh entropy. It's like I duplicate the system. Okay, I duplicate the system. And then actually the decoherence is like an interaction between the two copies, okay, between the duplicated two copies, okay? And as I said before, if I want to study the density matrix, okay, I can always turn the cat state to a broad state, okay, and map this into a double Hilbert space. And the decoherence becomes the interaction between the two copies of the system. Okay, so actually this is the general mapping. So any mixed state density matrix can be mapped to a pure state quantum state in the double Hilbert space. Okay, and the decoherence can always be viewed as an interaction between two copies. Okay, it turns out in this situation, the decoherence can drive a phase transition. Okay, can drive a phase. It's a pair condense, can drive a pair condense between the bound state of the Ising spin from top layer and the Ising spin of the bottom layer. Okay, so this bound state condensation is a spontaneous breaking from the double symmetry to a diagonal Z2 symmetry. Okay, and we also know that the disordered phase of a quantum Ising system in 2D is dual to the deconfined phase of toric code. Okay, deconfined phase of toric code. Okay, so this phase transition can also be interpreted as like the E-anion of the top toric and the E-anion of the bottom layer of toric, they form a bound state. Okay, and then they form then they condense. Okay, then they condense. So actually, so it's a decoherence-driven information transition. Okay, it's like if I turn on decoherence on toric, in the second radial entropy, I can drive this kind of phase transition. Okay, so the E-anion from the top layer and the E-anion from the bottom layer, actually they couple and the pair condense. Okay, this is information phase transition. Question?
What do you mean by diagonal?
Oh, diagonal symmetry means that I transform the two layers with the same action, right? Because actually, as I said before, diagonal symmetry means that I actually perform the symmetry transformation from the left and right simultaneously. It's like I actually perform symmetry action on the top and the bottom layer simultaneously. That's a diagonal symmetry. Okay, so this is about quantum critical point on the decoherence. Okay, so now let me try to move on to the topological states, starting with the chain insulator under decoherence. Okay. Yeah.
The last part of the
Yeah.
question, right? Can you consider different kinds of boundary conditions when you talk about the critical points? Can we imagine if you take Harvey states under the defects, what's the corresponding result?
That probably corresponds to some specific decoherence channel. Yeah, so we can talk about that later. That's a more detailed question. Yeah, right. So yeah, okay. Yeah, so let me try to finish this part. So yeah, okay. So let me first so let me say that I consider a chain insulator wave function defined on, for example, torus. Okay, without any boundary. Okay, just consider a chain insulator on a torus. Okay, and actually I want to consider this one. Okay, this actually trace the chain insulator density matrix times another density matrix, which is a trivial insulator density matrix. Okay, and in quantum information, this quantity is called fidelity. Okay, basically it compares how similar two density matrices are. Okay, so suppose actually just suppose that both rows are a pure state and they are the same density matrix, then actually trace row square will be 1. Okay, but normally it's something smaller than 1. Okay, so but this quantity is called a fidelity. And then I can take a log of this quantity. Okay, take a log of this quantity, and then this f equals to minus log z. Okay, actually is called the second relative radial entropy. Okay, second relative radial entropy. But actually, because I use the notation z and f, you probably can guess that I'm trying to map this quantity to be the partition function of something. Okay, and I'm trying to map this quantity to be the free energy of something. Okay, so I'm going to try to map this to be the partition function, and this is going to be the free energy. Okay, so what is this partition function? Okay, it's a partition function of what system? Okay, so now let's look at this density matrix of a chain insulator. So the density matrix of chain insulator in the path integral form, as I said before, can be viewed as performing the path integral. Okay, this is the tau direction. Okay, the tau direction. So I can view this as a performing path integral in space-time and evolving with a chain insulator Hamiltonian from tau equals 0 to tau equals beta. Okay, and then the other density matrix can be viewed as evolving, okay, with a trivial insulator Hamiltonian from tau equals 0 and tau equals beta. Okay, and then it means that there will be two interfaces, okay, between a chain insulator and a trivial insulator in the temporal direction. Okay, there are two temporal interface. Okay, two temporal interface. Okay, and now suppose I perform a space-time rotation. Okay, now you can imagine, then you can immediately see that actually the temporal interface will become a spatial interface. And as the spatial interface between the chain insulator and the trivial insulator, there will be chiral edge mode. Okay, there will be chiral edge mode. So there will be chiral edge mode on one interface and another chiral edge mode on the other interface. Okay, so eventually this Z becomes the partition function, okay, of a 1 + 1 dimension or 2 + 0 dimension non-chiral CFT. Okay, is that right? So even though both systems, okay, are fully gapped systems without any spatial boundary. Okay, let's say that I define my system on torus without any spatial boundary. As long as I take a trace of one density matrix and another density matrix, then this quantity, the fidelity, is mapped to the partition function of a boundary CFT. Okay, boundary CFT. And also the decoherence, as I said, suppose I decohere the chain insulator, the decoherence is mapped to the interaction between the two interfaces. okay, interaction between the two interfaces. So this is something new and actually do not really happen in charismatic physics. So in charismatic physics, suppose I take a chain insulator, normally the two boundaries, they don't talk to each other. Okay, but here, they naturally talk to each other. Okay, they naturally talk to each other because of decoherence. Okay, decoherence will become the interaction between the two temporal boundaries. Okay, so now let's think about something very simple. Okay, so let's say that I have a chain insulator with a chain number equals to 1. Okay, with chain number equals 1. Then without any decoherence, then actually this guy will become the partition function of a 1 plus 1D non-interacting Dirac formula. Okay, is that right? And with central charge equals 1. Okay, central charge equals 1. Okay, but now suppose I turn on some decoherence, and now the question is that what kind of symmetry I want to preserve. Okay, suppose I want to preserve the double U1 symmetry. It means that I preserve the U1 symmetry of the left moving fermion and another U1 symmetry of the right moving fermion. As long as I preserve U1 symmetry of the chiral fermions, there's no way any interaction can gap out this 1 plus 1D Dirac formula. Okay, is that right? Because both U1 symmetry are anomalous. Okay, so there's no way to gap them out. So it means that as long as the decoherence channel preserve the double symmetry, this quantity will always correspond to the partition function of a 1 plus 1D CFT. The only thing that can change is some Lagrange parameter. Okay, but this quantity will always become the partition function of 1 plus 1D CFT. And F will always become the free energy of the 1 plus 1D CFT, maybe with a non-trivial Lagrange parameter. Okay, but now let's consider a slightly more non-trivial example. Okay, let's say that I consider a situation where the Chern number equals to 2n. Okay, Chern number equals 2n. Then actually on each boundary, there will be 2n chiral fermions. And eventually, without any decoherence, this Z will become the partition function of CFT, which is the U2n level 1. Okay, U2n level 1, basically just the 2n copies of free non-interacting Dirac fermions. Okay, okay, so now the decoherence, okay, becomes interacting between the left moving mode and right moving modes. And it may reduce the U2n level 1 to some other interacting CFT, depending on the symmetry of the decoherence. Okay, so let's say that I choose to weakly measure the SU2 subgroup of the U2n. Okay, weakly measure the SU2 subgroup of the U2n. And I preserve the diagonal SU2 symmetry rather than the doubled SU2 symmetry. Okay, then it's like I'm actually allowing the current of the SU2, the left current of SU2 times the right current of SU2. And this interaction can be marginally relevant, and it can gap out the SU2 part of the whole system. Okay, so it means that actually we have this kind of a famous decomposition. U2 and level 1 can be decomposed into this coset CFT. And this SU2 current interaction induced by decoherence can actually gap out this part of the CFT. Okay, and gap out this part of the CFT, and we are left with interacting CFT with a non-integer central charge. Okay, with a non-integer central charge. Okay, so this means actually this fidelity now, under decoherence, depending on the decoherence, the symmetry, I can get some very non-trivial CFT here, some interacting CFT here. Okay, with some non-integer central charge. Okay. Okay. So now the question is, how do we see the central charge? Okay. How do we see the central charge? So we can just borrow what was known from the CFT literature. Okay. So let's say that I define both systems, the chain insulator and trivial insulator. Both of them are defined on a cylinder. Okay. Both of them are defined on a cylinder. Okay. And we can calculate the free energy density along the y direction and try to calculate how it scales with the perimeter of the cylinder. Okay, then based on the old work by Carty, we know that the leading order will be a non-universal term proportional to the length of the perimeter of the cylinder. But then they say a subleading term, but the subleading term, and the coefficient of the subleading term is precisely the central charge. Okay, precisely central charge. So it means that at least numerically we can check the prediction. Okay, we take a chain insulator and turn on decoherence, and take it out and take the fidelity against a trivial insulator, and I can do the finite size scaling. I should be able to see this as central charge. Okay, at least we can check numerically the prediction here. Okay, so well, in addition to the central charge and everything, okay, we can also look at something more detailed. Okay, so look at something in more detail. So actually, let me first introduce a notion that we played with a long time ago, okay, about 10 years ago now. So 10 years ago, actually, we kind of think, or we thought of a notion which is called a strange correlator. I'm sorry, actually, we were not good at the names back then. So strange correlator is probably not a very good name, but still. Okay, it look like this. Okay, look like this.
Let me ask some questions.
Yeah, okay.
Maybe 2 slides back.
Yeah.
So I think you try to say there's a decoherence interpretation of the interaction in the H states of the
Yeah, I think it's better to say there's interaction interpretation of decoherence. Yeah.
But so how are you going to do this in the system? Is that you do some measurement, or do you try to write down the interaction to implement this on the system?
Well, I mean, we don't really need to know the exact form of the interaction, right? As long as we know the interaction, we know the interaction. Sorry, as long as we know the symmetry,
Yeah, symmetry.
of the decoherence, the symmetry will, map to some interaction term. Then we can run the RG of the interaction term, which actually is some very standard procedure. And we know that with certain sign of the interaction, it can be marginally relevant and gap out this part of the CFT.
Okay.
Yeah.
So then you just say demand the symmetry. Any possible interaction, preserve that symmetry. That would be
Yeah. Right.
Okay.
Yeah. That's. I mean. Yeah. So. Yeah. The RG in 1+1D actually is pretty standard, and we don't really need to know that much about the interaction. The symmetry actually is is the most important thing to determine the fate of the RG flow. Yeah. Okay. So I was trying to introduce this notion of strain correlator. So basically.
Just one comment.
Yeah. Okay.
Sometimes depends we demand the symmetry in which precise way. Sometimes we may just say we assign character and preserve that symmetry, but maybe the fate of that symmetry within interaction still can drag to different fates, right?
It can, but actually there are not many possibilities actually.
Okay.
Yeah, there are finite number of possibilities. I mean, there are infinite numbers of microscopic parameters, but there are finite numbers of possibilities in the IR. I think this already.
In the sense of the symmetry match generation, SMG interaction.
I know. Yeah, that's a story which we are actually, yeah, right. So to what extent does the decoherence, behave like interaction? Can it behave like a SMG? That's something we are studying very hard right now, but actually I don't have a very solid answer to that yet. Yeah, indeed. Yeah, right. I agree with you. I mean, yeah, there are possibilities which still is a mystery in this formula.
Yeah. So there could be more refined class of the symmetry preserving decoherence or something. Refined in the sense there are several subclasses.
Yes, right. Yeah, but normally, I mean, so SMG is really a very exotic, example. Normally in field theory, once we know the symmetry, there are finite number of fixed point or phases that we can go to, right? So we already narrowed down from a huge parameter space to a finite number of options. So yeah, I think this already tells us a lot about the system. Yeah. Right. So yeah, right. So I was trying to introduce this notion. So basically, the goal of this notion is the following. So let's say that someone gives me a wave function of a quantum many-body system, psi. Okay, this psi is a wave function, and actually, so let's say this wave function generated from DMRG, for example, some numerical method. It's a wave function of many-body system, and we know it's a symmetric state, which means that if I measure all the correlation function in the short range correlating, okay. But knowing this is a disorder state still leaves up a question of whether this is the SPT state or it's a trivial state. Okay, whether it's wave function SPT state or trivial state. So, to diagnose whether this wave function is a trivial state or SPT state, basically, this is something that we can calculate. Okay, we can calculate this psi and 2 operators separating space and omega is the trivial state. Okay, we can always construct a trivial state. Okay, and in this quantity, using the space-time evolution picture, we can view this quantity as psi evolving, okay, with the SPT Hamiltonian along the time direction, imaginary time direction, and omega is a state evolving with the trivial Hamiltonian, okay, backwards along the imaginary time direction, and then they have an interface. Okay, they have interface in temporal direction at tau equals 0. So this strain correlator really is the correlation function as the temporal interface between the SPT phase and the trivial phase. So this means that suppose psi is really a non-trivial SPT phase, then this quantity should be non-trivial. Non-trivial meaning that this quantity should be either long range or powerful. Okay, at least this should be true in 1D and 2D. Okay, because 3D is possible that the boundary can have topological order, and this cannot be diagnosed with the correlation function. Okay, but at least this should be true in 1D and 2D. Okay, between 1D and 2D. Okay, yeah, right. So basically, yeah. So let's first check this idea. Okay, let's first check this idea. Okay, so let's say that we start with a one-dimensional, simplest one-dimensional SPT phase with a Z2 cross Z2 symmetry. Okay, let's say that. So this is the Hamiltonian for the one-dimensional system with Z2 cross Z2 symmetry, and actually the green Z2 means the Z2 symmetry on the even sides, and the red Z2 is the Z2 symmetry on the odd side. Okay, and I turn on a transverse field because actually I want the system to have some finite correlation length. Okay, I don't want to the system to be an artificial limit. Okay, so let's look at the solid red curve first. Okay, the solid red curve. So actually, you can show that. So I mean, this can be easily computed using a numerical method. You can show that indeed this strain correlator indeed actually has a long range correlation. Okay, has a long range correlation. Okay, so this is the strain correlator for the ground state of the Hamiltonian. Okay, and as long as when h is smaller than 1 or 1/2, I forgot. As long as h is smaller than some critical point, this state will always be, this Hamiltonian will always be in the SPT phase with a Z2 cross Z2 symmetry in 1D. Okay. Okay. So that was the previous version of the strain correlator was a strain correlator for the pure quantum state. But now let me talk about the density matrix. Okay, because we want to talk about density matrix, the mixed state density matrix, so we need to generalize the strain correlator into the form which involves density matrix. So there are two generalizations. Okay, there are two generalizations. So one generalization is trace rho SPT, so two operators and the rho naught. So rho naught is the trivial state density matrix. Okay, so in the space-time form, in the space-time formalism, you can see that actually again the trace rho will have two interface in a temporal direction, and then this strain correlator is like I insert operators at one temporal interface, but not the other. Okay, so we call this as the type 1 strain correlator for the mixed state density matrix. Okay, but we can also insert the order parameter or the operator at both temporal interface. Okay, at both temporal interface, and then this is called type 2 strain correlator. Okay, type 2 strain correlator. So now let's check how they work. Okay, so let's say that I return to the original model. Let's say I return to this model again. I start with a system with a 2Z2 symmetry, but I turn on decoherence on the even side. It means that actually I want to break the doubled green Z2 to a diagonal green Z2. Okay, so eventually for the density matrix, I only have one green Z2, but I still have two red Z2. Okay, the green Z2 is diagonal, but the red Z2 becomes a double Z2. Okay, then in this case, let's check what happens for the strain correlator. So it turns out that as long as I have a small decoherence, okay, the type 1 strain correlator will become short range. Okay, it means the type 1 strain correlator is unstable. Okay, it's unstable against a weak decoherence. Okay, against a weak decoherence. This actually is consistent with a lot of previous study about the string operator. Okay, so actually there were previous study about using the string operator to detect a decoherent SPT state, and the conclusion is always the string operator will just fail. Okay, will become short range once the system has a weak decoherence. So it turns out that actually Zhang Yang showed that the type 1 strain correlator is actually directly related to the string operator of the one-dimensional SPT. So that means that our finding, which is the type 1 strain correlator being short-ranged with decoherence, is consistent with the fact that the string operator being short-ranged under decoherence. Okay, but surprisingly, the type 2 strain correlator is still robust. Okay, type 2 strain correlator is still robust under decoherence. Okay, so this means that actually, the original SPD state with a Z2 cross Z2 symmetry, once they turn on a little bit of decoherence on one of the Z2 and break the double Z2 to a diagonal Z2, okay, the system will still remain that it was once the SPD state. Okay, the SPD state is not completely destroyed, but to see that, we need to use the type 2 strain correlator. We cannot use the string operator. We cannot use the type 1 strain correlator. We need a type 2 strain correlator to see that. Okay, and we can also show that numerically that actually, suppose I turn on the transverse field. Okay, the type 2 strain correlator will go to 0. Okay, when the transverse field is actually greater than some critical value. Okay, so this actually is going to be a SPD to trivial phase transition. Okay, so actually the strain correlator also precisely captures the critical point of the SPD to trivial phase transition. Okay, so these are numerics.
Sorry,
Yeah.
Couldn't see the decoherence, so I think maybe one slide earlier.
Yeah.
The type 1 and type 2 in the caption.
Right. Yeah. So the type
0, 1, but I didn't see that. What's the curve for the?
for yeah right.
Yeah,
So the
before curve. Right?
no these two are on top of each other. They overlap with each other completely.
And P value for the.
P is a decoherence strength.
Okay.
That's the decoherence strength.
So 0 means weak.
0 means no decoherence at all, just a pure state. So P equals to 0.1 means that there's some weak decoherence. So you can see that type 1 strain correlator is actually become short range even with a weak decoherence, but type 2 strain correlator is still long range. Yeah. Right. But actually, but both.
Okay, but then the third and fourth in the caption is that P equals 0 and 1 or this 1. Right?
Say again?
You have a type 1, type 2 in the third and fourth lines in the caption. Is that P equal to 1 and or P equal to 0 and 1? Yes.
P to the 0.1.
Oh, 0.1, sorry.
This is distance.
Okay.
Yeah, this is distance.
Yeah.
Yeah, this is the distance. And this is the plot of the saturating value versus P. Sorry, versus H. Right. So it means that when H is smaller than 1, so for type 2 strain, for example, it always saturates to a finite value for the long distance, but the saturation value will go to 0 at the H equals 1. Yeah. Right. Okay, so yeah, this was numerics. So can we have a simple physical picture or not? Okay. So now, as I mentioned before, so everything happens as the temporal boundary. Okay, a temporal boundary. So actually, we can do a space-time rotation and think about the space boundary, which actually is a lot more intuitive. Okay, it's a lot more intuitive. So for a one-dimensional SPD phase, the boundary, the spatial boundary, is just spin and a half. Okay, it's a very simple spin and a half, which carries a projective representation of Z2 cross Z2. Okay, so basically, the decoherence is mapped to some interaction between the two boundaries, between the two spin and a halves. Okay, so one spin and a half will carry a Z2 cross Z2. The other spin and a half will carry another Z2 cross Z2. But suppose I actually break the diagonal, if I break the doubled green Z2 down to a diagonal green Z2, but I still keep the red Z2, okay? Still keep the red Z2. The Hamiltonian will look like this, okay? The interacting Hamiltonian, which is the effective Hamiltonian effective representation from the decoherence, will look like this. Okay, imagining the green Z2, okay, imagining the green Z2 is a Z2 which I can rotate by pi along the x-axis. But the red Z2 is a rotation by pi along the z-axis. Okay, if I break the diagonal, so if I break the double green Z2 down to diagonal green Z2, but I keep the double red Z2, this is the only Hamiltonian I can write down. Okay, but then you can immediately see that this Hamiltonian still has the non-trivial degenerate ground state. Okay, for example, when J is smaller than 0, the ground state will be either this or this. They are doubly degenerate. It means that this inter-boundary interaction cannot trivialize the full boundary spectrum. Okay, cannot trivialize the full boundary spectrum. However, to see this, we cannot just calculate the correlation function at one boundary. Okay, because if I calculate the spin-spin correlation, the time direction, spin-spin correlation at one boundary, I will still see short-range correlation because the spin-spin correlation at one boundary cannot connect this ground state to this ground state. Okay, to see the degeneracy, I will have to calculate this correlation function. Okay, it's actually double correlation function at both boundaries. And this correlation function after space-time rotation is precisely the type 2 strain correlator. Okay, precisely type 2 strain correlator. Okay, is that right? Okay. Yeah, so this is the one-dimensional situation. Okay, suppose we consider a two-dimensional situation. It's much harder to do numerics, but luckily we can still have some field theory kind of understanding. Okay, field theory understanding. So for example, let's consider a two-dimensional SPD state with U1 cross U1 symmetry. So it turns out that we can write down a approximate or schematic wave function for the U1 cross U1 SPD state. Okay, the wave function looks like this. It's a superposition of all the configurations of a 4-component unit vector n. Okay, n is a 4-component unit vector, but there's a weight. Okay, there's a weight, and this weight is a 2 plus 0 dimensional Western-Witten model. Okay, 2 plus 0 dimensional O4 non-sigma model with a Western-Witten term. Okay, it looks like this. Okay, this is the work done by me and Central also about 10 years ago. Okay, also about 10 years ago. Okay, so now you can immediately see that suppose I want to calculate a strange correlator. Okay, strange correlator. Then actually strange correlator becomes calculating the ordinary correlation function of a 1 plus 1 dimensional O4 non-sigma model with the Western-Witten term, which is the conformal field theory. Okay, which is the conformal field theory. So this tells us that actually, at least for this pure state SPD state with the U1 cross U1 symmetry, the strain correlation should be power law correlation. Okay, should be power law correlation because this evaluation of the strain correlation is mapped to the correlation function of a conformal field theory. Okay, of conformal field theory. And actually, with a U1 cross U1 symmetry, this conformal field theory is precisely a Latino liquid with this description and its dual. Okay, the theta and the phi are just the two U1 rotors, which rotates under the two U1 symmetries. Okay, under two U1 symmetries. Okay, so now let's try to evaluate what happens under decoherence. So again, we started with a green U1 and a red U1. Okay, green U1 and red U1. Okay, and actually the pure state density matrix will have a 2 green U1 and a 2 red U1. Okay, but now let's say that there's a decoherence which breaks the doubled green U1 to a diagonal green U1, but I still keep the doubled red U1. Okay, doubled red U1. Okay, so this means that I make 2 copies of the system. Okay, theta and theta prime and phi and phi prime. But the symmetry now allows me to turn on this term. Okay, turn on this term because actually I break the doubled green U1 down diagonal green U1. So it allows me to turn on a term which is cosine phi minus phi prime. Okay, this term is invariant onto the diagonal green U1 symmetry, but not invariant on the double green U1 symmetry. Okay, is that right? And then turns out you can see that actually, okay, so this operator, when it's actually relevant, okay, it's going to gap out the channel, which is theta minus theta prime and phi minus phi prime. Okay, but there will still be a gapless channel, which is theta plus theta prime and phi plus phi prime. Okay, the plus channel will remain gapless, but the minus channel will be gapped out. So that means that this decoherence is mapped to an interaction which gap out a part of the doubled boundary, but leave the other part gapless. So the system still have a conformal field theory. However, to see the gapless CFT on the decoherence, we cannot just use the old strain correlator. We have to use the type 2 strain correlator. Okay, we have to use the type 2 strain correlator. Okay, to see that. Okay, so actually this is a more looking into more details of the decoherent SPD state. Okay, so yeah, right. So I can just stop here, or I can continue with the last little story. So
6 p.m.
Okay, 6 p.m. Okay, nice. Okay, so higher form symmetry. Okay, under weak merriment. Okay, under weak merriment. So basically, we know there's a lot of generalized symmetry notions in the last few years. In the higher form symmetry, and there's a categorical symmetry. There are many different symmetries have been created. Oh, also subsystem symmetry, of course. I mean, all these notions have been created. Okay, so basically, the higher form symmetry, although we call it higher form symmetry, it actually can be very different from zero form symmetry in many ways. Okay, so for example, suppose I consider a spontaneous symmetry breaking state, okay, of a zero form symmetry. Okay, ordered state of zero form symmetry. We know very well that suppose actually we have a continuous zero form symmetry breaking, this is going to be Goldstone mode. But this Goldstone mode is going to be very unstable under explicit symmetry breaking. Okay, once I weakly break the zero form symmetry, I'm going to immediately gap out the Goldstone mode. Okay, and gap it out to be a pseudo Goldstone mode. It will acquire a small mass. But this is not true for the higher form symmetry. Okay, suppose I have a spontaneous breaking of a one form U1 symmetry. I'm going to have some photon mode, which is the Goldstone mode of the one form symmetry. However, even if I break the U1 one form symmetry on the lattice, okay, as long as I weakly break it, okay, it's not going to gap out the Goldstone mode. Okay, it's not going to gap out the Goldstone mode. Okay, so that means that actually the zero form symmetry and a one form symmetry or higher form symmetry have some sharp difference. Okay, have some sharp difference. Okay, in some sense. So now the question I want to ask is that are they also different under weak merriment? Okay, are they also different under weak merriment? Okay, so for example, let's consider a simple zero form symmetry. Okay, simple zero form symmetry. Let's consider a zero form Z2 symmetry and consider a spontaneous breaking state of the zero form symmetry. Okay, this is the state. Okay, just a zero form symmetry is X. Okay, it's just X operator generates Z2 symmetry, and this state obviously is going to be a spontaneous symmetry breaking state with all spin polarizing to be upspin. Okay, so now let's imagine I want to measure the X operator. Okay, I want to measure the X operator because if I measure X operator, if I just projectively measure the X operator, it's going to restore the symmetry. It's going to actually make all the spin equals to X equals to one spin. Okay, it's going to restore all the symmetry. However, as long as the merriment is not projective, as long as there's a small chance for the system to be not measured, okay, then I'm not going to restore all the symmetry. Okay, I'm not going to restore all the symmetry. Okay, or in other words, actually we can take the space-time picture. Okay, the weak merriment is like performing something as the boundary. And the bulk is ordered. Okay, we know very well that suppose the bulk is ordered, there's going to be a very big proximity effect to induce the boundary order as well. Okay, it's just like suppose I put a two-dimensional material on a three-dimensional superconductor, the 2D material will also have some proximity superconductor. Okay, because the superconductor spontaneously breaks some U1 zero form symmetry is going to have a very strong proximity effect. Okay, so this means that the zero form symmetry spontaneous breaking can be very robust against weak merriment. It can only be restored or it can only be affected by projective merriment. Okay, in order to restore the symmetry. But a one form symmetry.
Yeah, quickly, maybe a few more quickly. Just make sure the comparison for zero form symmetry versus one form of other symmetry that you are trying to say here the Goldstone modes, if it's spontaneous broken, still gapless and become gapful, it's basically broken, right?
For zero form symmetry, yes.
And for one form symmetry here, you try to imply the, let's say, photon of the U1 is more robust than
against the UV breaking of the one form symmetry. Yeah. So or you can say that there's still an exact one form symmetry emerging in the IR.
Right.
You can also say that. Yeah.
Right. We know the Higgs mechanisms can still give a
sure, but that means you break that in the IR.
Right.
Yeah, it means you break the one form symmetry in the IR. But actually, if you just weakly break the one form symmetry in the UV, the IR emergent one form symmetry will still be exact.
Another question I have to ask earlier before you summarize previous part, you actually asked now.
Okay, yeah. Sure.
Just one slide earlier. I think you say the type 2 strength correlator detects some mixed anomaly of the 3U1 in one part 1D.
This is this is no, this is a 2D SPT.
Okay.
Yeah, 2D SPT. It's not 1+1. So it's the strand correlator is mathematically mapped to correlation function 1+1 is CFT, but it's actually probing the anomaly from a 2D SPT.
Yes, but anomaly is in 1+1D.
Anomaly is in the 2+0 dimension. Temporal boundary is a 2+0 dimension.
SPT is in 2+1D.
Yeah.
To the SPD, 2D space.
But actually, the cohomology classification, for example, is
Right.
classifying the action in the 2+1D space-time. So both the spatial boundary and the temporal boundary should inherit the anomaly from the bulk.
Okay, my point is that I think the anomaly class is H3, so the cohomology
Yeah.
group.
Exactly.
Then I don't think there's a mixed one between 3 U1, unless the U1 becomes this frequency M.
Why? Well, if there's a mixed anomaly between 2U1, why there cannot be mixed anomaly between 3U1?
Because you cannot write the cup.
Okay, that's fine. That's fine. I mean,
Yeah.
I'm just saying there is an anomaly between green U1, I mean the one green U1 and this red U1, and also the green U1 with that red U1. I'm not saying there's a mixed anomaly between all three of them.
I see.
You know, basically, I mean, you can imagine that you cannot write down a Chern-Simons term of 3 gauge field, right?
Right.
But actually, you can write down 2 Chern-Simons term between 3 gauge field. This is what I'm saying.
Okay, so
Yeah.
there's some mixing between maybe
Yeah, right.
2 subgroup, but 3.
Yeah. There's a mixed anomaly between these two and also this and that.
And why is that spatial for the unique for the type 2 correlators? How do I see the relator?
Because actually, as I said, the type 1 strand correlator will always be short range because actually this guy gaps out the theta minus theta prime and the phi minus phi prime channel. If you just calculate the correlation function between e to I theta, e to minus I theta, it will be short range because you can just see that e to I theta, e to minus I theta. This involves both theta plus theta minus. Right, sorry, plus, sorry. See. This is 1. Yeah, right. Yeah, something like this, right? Yeah, so it means that as long as the minus channel is actually gapped out, this actually will be short range, and this is type 1 strand correlator, right? To see the type 2, to see the gaplessness of the CFT of the residue CFT, you will have to calculate theta 1 plus theta 2, which is just a theta plus channel. Right, so that's a type 2 strand correlator. Yeah, so type 1 strand correlator will just be gapped out because a part of the CFT is gapped out.
Okay, thanks.
Yeah, okay. So, as I said, yeah, right. So basically, from the bulk boundary correspondence, okay, so when the bulk is actually a strong order, okay, so strongly breaks on zero form symmetry. No matter what we do as the boundary, okay, it's going to be very hard to restore this boundary symmetry or drive any transition as the boundary because there's a big proximity effect from the bulk. But the situation can be very different. Suppose the bulk is a photon phase. Okay, suppose the bulk is a spontaneous symmetry breaking phase of a U1 one form symmetry. Okay, let's imagine the 3-dimensional system. So let's imagine we have a 3-dimensional system, and there's a U1 magnetic one-form symmetry. Okay, U1 magnetic one-form symmetry, and the bulk is a spontaneous breaking phase of the U1 magnetic one-form symmetry. Okay, and I can weakly measure. Okay, I can weakly measure, for example, the kinetic energy of the charge. Okay, of the photon. Okay, kinetic energy of the charge of the photon. And based on the bulk boundary correspondence, and this weak measurement can be mapped to some boundary action. Okay, some boundary action. And this actually, you can either view this as a 3+0 dimension action or a 2+1 dimension action. So both are okay. Okay, but the important thing is that this phi describes the charge, the matter field of the U1 gauge field. Okay. But then the U1 gauge field as the 3+0 dimension actually will have a non-local term here. This is from integrating out the bulk. Okay, integrating out the gapless bulk, I'm going to get a non-local interaction as a boundary. Okay, non-local Maxwell term as a boundary. So this interaction, so this theory has been studied a lot. in the last decade because of the duality wave. Okay, so it turns out this theory has a self-duality. Okay, has an exact self-duality. Okay, strong weak duality. Okay, so and there's a line of fixed point. Okay, so this theory is precisely due to another theory, actually with actually E changed to E2 with this value. Okay, it's a line of fixed point. So it means that actually, suppose I have a spontaneous breaking of a one-form symmetry in the bulk, the weak merriment can indeed drive some transition. Okay, and this transition can have a self-dual kind of structure, and as a self-dual point, there's a lot of things we can calculate simply because of the self-duality. Okay, simply because of self-duality. So there's a big difference between the one-form symmetry and the zero-form symmetry under the weak merriment. Okay, under weak merriment. Okay, so let me try to summarize. So basically, I try to introduce the field theory formalism to study some quantum information problem, in particular, the problem of decoherence and weak merriment. Okay, so I try to introduce the long wavelengths or IR limit description for this kind of problem, and I try to map everything to the boundary problem of a topological field theory or the conformal field theory. Okay, so it turns out a lot of universal results actually can be obtained using this approach. Okay, so obviously there are some other open questions worth exploring because, like for example, the boundary physics is interesting, but actually when there are two different boundary effects interplay with each other, the situation can be even more interesting. So for example, suppose I consider a quantum critical point between the SPT state and the order state. Okay, then there are two different boundary physics at play here. One is the boundary physics from the SPT, from the anomaly from the bulk. The other is the boundary physics coming from the critical mode in the bulk. Okay, so this actually will be a very, very interesting scenario. Okay, so let's imagine I create I prepare an initial wave function, which is the wave function as the critical point between SPT state and order state, and perform weak merriment. Okay, then it means that this problem is mapped to a very non-trivial boundary problem. Okay, with two different boundary effects interplay with each other. Okay, another situation is that I've considered the Wilson-Fisher critical point under decoherence and weak merriment, but a Wilson-Fisher fixed point is a conventional quantum critical point, which can be mapped to a classical Principal-Landau theory. But we know that there's another large class of a quantum critical point called the deconfined critical point with a fractionalization, okay, which does not have a good Principal-Landau description. Okay, so this kind of a theory, we can also ask what happens to it under weak merriment. Okay, this is something that we can explore in the future. Okay, so yeah, this is the end of my talk. So thank you for staying here for this long. Okay, yeah, and also thank you for everyone staying on the Zoom.
Thank you, Cenke. Thank you for the wonderful lecture seminar. Question, comments?
Firstly, I wonder, like, when you always mentioning like the weak measurement, does it mean that only when the p is very small, you can like incorporate?
Oh, actually, so the weak merriment simply means that it's not a projective merriment. Yeah, it does not have to be extremely weak. So it's a phrase people use to describe a non-projective merriment.
Yeah.
So you don't show some state in Hilbert. Like,
Sorry?
You don't show some state in the Hilbert space. In the projection, you'll show some states in
Well, in the projection, we just in the projective merriment, we just collapse the wave function completely, right? So here, actually, we don't do that. We just say there's some probability for the system to collapse, some probability that it does not collapse.
So P can be not small.
Can be not small. Yeah, it's like when we do RG, right? I mean, we do perturbative RG, but sometimes the result actually can still be okay when the coupling constant is not that small. You know, so.
Why we don't? Why we don't do projective?
Because it's going to be slightly boring. Because then the result will be pretty simple, right? So, for example, I have an Ising system. You know, then I just measure every Ising spin. Then the state will become a product of the merriment outcome, right? Just a very simple wave function. It's going to be a very simple problem. Yeah, so weak merriment actually gives you a lot of possibilities.
So here that the technology of weak measurements, don't necessarily mean
Oh yeah, I don't necessarily mean extremely weak. I just mean not projective.
just some pure react, which is not projective.
Yeah, right.
So in your interpretation, like a big measurement just introduce some like temporal interaction boundary.
Yeah.
So the non-trivial parts are always actually somewhat scale is non-trivial boundary.
Yes, yeah, right. Yeah, suppose you have a system with very trivial boundary, then it probably does not really have much interesting thing going on the Decoherence. So,
I was thinking about another question, like how to define something like polyoperator or stabilizers like a conjunctive theory system. So do you think that you can follow interpret some like poly X or poly Z as some kind of like so
well, I mean, yeah, see, so the path integral field theory is a very coarse-grained way of describing system, right? So basically, when in field theory, so sigma X, sigma Z, they will just become some operator in the field theory with the same symmetry. So it will not preserve the algebra between the sigma and sigma Z. So if the algebra is very important to your study, then this approach probably cannot capture that physics. Yeah, this approach captures the physics which is sensitive to symmetry, but not the algebra. Yeah, right.
are there question comments from the audience on Zoom online? Okay, now we should give a big applause to Professor Smith again. Thank you very much.
Thank you.